Okay. So, basically, we think that everything in the universe is either matter or, what do you think? Something we can't hold on to, but it influences us. And we studied it a lot last semester. Energy, yeah. Everything in the universe is either matter or energy. And the two interact quite a bit, huh? It also turns out recently we've discovered some really weird stuff that we don't know exactly what it is, called dark matter, as well as dark energy. And we're still learning about this. But when we do our calculations of the universe, for instance, and we measure the mass of a galaxy, we can tell how heavy it is by its gravity, right? The heavier, the more gravity it has. Well, these galaxies have too much gravity. So there's something missing, and we're calling that dark matter. At any rate, we're going to focus on regular matter at this point. So let's go to our project. And like I said, put your name on it. Put your name on the file name. I don't know if you've noticed or not, but I am subtracting points when you fail to put your name either on the project or on the file name, right? Yes, ma'am. Uh-oh. Because you have, it just won't even download? Okay, it says it's saved to the downloads folder. Oh, you've got like 3 of them. Right click on one of those.
The project?
Right,
oh,
right. Atoms in the periodic table. Right click on it.
And then the kitchen one.
Well, it wasn't called Crime in the Kitchen. It was called Properties of Matter. It was the formal title of it. Maybe that's why you were looking for some. I was calling it one thing, but the title was another thing, huh? Okay, so let's start by looking at this on the front. And why is this on the front? Why is this piece of art the cover here? Armando, what do you think? What is this image showing? Yeah, it's showing an atom. Okay, it's showing the nucleus. Where is the nucleus on here? Describe the nucleus for me. This big old thing in the middle is the nucleus, huh? Well, then what are these little things that are whipping around it? The whole thing is an atom. The nucleus is the center of the atom, and it is orbited by electrons are orbiting the nucleus. Now, let's talk about this word nucleus for a minute. The word nucleus means the core or the center of something. And I've seen many students mix up the word nucleus when we're studying atoms with the same word nucleus when we're studying cells. They're both the center or the core of those things, but they're different things, aren't they? Right? So be careful with that. Like if I ask you for a definition of nucleus, don't tell me that it's the control center of the cell in this class, but do use that definition in biology, huh? Right? In this class, it's the center of the atom made of protons and neutrons. Are we good on that? Next, if you look down in the yellow writing, I don't know if you've seen these before, but we have a series of what are called standards or goals or objectives, which are what every student is supposed to achieve in each class. And these come from the state of Nevada. And this means high school, physical science, goal number 1, part 1. Okay, so this is our standard. This is what you're supposed to know before you graduate, which basically means once you finish this class. which basically means once you finish this unit, you should have this standard under your belt. Use the periodic table as a model. So it's not just look at the periodic table, it is make use of it. Use the periodic table as a model to predict the relative properties of elements. So you're going to use the periodic table to predict the properties of the different elements. How are you going to do that? You're going to base your prediction on the patterns of electrons in the outermost energy level of the atoms. We're going to talk more about what an energy level is, but the important thing is that the behavior of an atom depends on the electrons. And not just any electrons, the ones that are orbiting on the outside. There's layers of orbiting electrons. Some are close to the nucleus. Remember, we talked about the excited atom, right? And some are farther from the nucleus. And those ones that are further from the nucleus are the ones that are really important to determine the properties of that element. That's why the baking soda behaved differently than the baking powder, which behaved differently than the cornstarch, because of the electrons in the outermost shell. Okay, so that's a big idea. And it's not just an idea, it's also a skill that you're going to develop, huh? Making use of the periodic table to make your prediction about the properties of the elements. It's okay. All right, let's move on to page 2. At the top of the page, it gives a couple other big ideas, and those are repeated on every page, right? The periodic table organizes the elements according to their properties. It's not just random. And then we have this big question: what are the characteristics of an atom? Now, sometimes it helps to look back at how people's ideas of things have changed over time. So we're going to do some reading, which means we're also going to do a little highlighting as we go, right? So here we go. Oops, I didn't mean to do that. History of ideas about the atom. Throughout human history, different cultures have contributed to our understanding of nature, ourselves, and the universe. Although scientific analysis may not support all of these historical ideas, it can still be useful to examine the development of our modern understanding. By looking at how our explanations of the world have changed over time, we can improve our own ability to analyze data, use logical reasoning, design valid experiments, and so on. So let's take a moment to survey the growth of our ideas about the most fundamental basis of matter, the atom. I should have said this a moment before. Sometimes when I'm scoring your highlighting, you don't highlight enough. Sometimes you highlight too much. How do you find that zone where it's just right? Well, there's probably, not always, but probably something important in every paragraph, but not the entire paragraph should be highlighted. Are you with me? You want to pick out the most important things from each paragraph. All right, so look for the most important stuff, highlight that. Most paragraphs will have something important, otherwise they wouldn't even be there, huh? Let's move on. Second paragraph. We'll start our exploration with Aristotle, a Greek philosopher from about 350 BCE. So in the last 10, 20 years, maybe more, people have started counting time a little differently. It used to always be BC, before Christ, and AD, which is Latin for the year of our Lord. But that really puts the focus for all human history on one religion, doesn't it? And to be more balanced, they've changed these things to BCE, before the Common Era. And the numbers are the same. The numbers haven't changed. It's just we're calling it before the Common Era. And now instead of this being 2021 AD, it's 2021 CE, the Common Era. So that's why this says BCE. So Aristotle's ideas about many topics were accepted for over 1,000 years, including his explanation that all matter was composed of a mixture of just 4 elements: earth, air, fire, and water, as shown in the diagram. Our explanations today are still based on his thought that different materials consist of a variety of simple components that are combined in different amounts. So Aristotle thought everything was made of earth, air, fire, and water. For instance, the human body. It's different combinations, though. So what about blood? That would be largely, but not entirely, it would be largely what? Water. What about bones? Largely earth. What about your breathing? What about your breath? And what about the fact that our bodies are warm? That's the fire, right? So we combine these 4 things together in Aristotle's ideas. And in a way, it's not that different from us saying today that our bodies are made of different atoms combined together, right? Different combinations of atoms give our bodies their characteristics. Another early Greek philosopher from about the same time, maybe slightly earlier, his name was Democritus, and he gave us our first idea of the atom. In the Greek language, atom means without cutting or unable to be cut. So anytime you put a in front of a word, it means without that thing. If you put a in front of a word. So would you like to be a homework? A means without that thing. So what's a homework? It means without homework, right? So tomy, T-O-M-Y, means to cut something. So for instance, you know that a lobotomy is when they cut out one of the lobes of your brain. A lobotomy. So atom means without cutting, or it can't be cut into smaller pieces. It's indivisible. It's a fundamental particle, according to Democritus. He thought all matter was made of tiny particles that could not be cut into smaller pieces. We still define an atom as the smallest piece of a substance that still has the properties of that substance. However, we also know that atoms themselves are made of even smaller particles. So today we know that an atom can be cut apart, but once you do that, it no longer has the properties of that substance anymore. For the next several centuries, Europeans considered Aristotle to be the authority on anything that was not included in the Bible. His ideas were unquestioned and untested, and they were passed on from one generation to the next. Is that using science if we're not testing the ideas? Right? With science, we always want to test our ideas. We want to make a hypothesis, make a prediction, design an experiment to test it. Ideally, your experiment is attempting to disprove your hypothesis. At any rate, after several thousand years, well, I should say 1,500 years or so, at the same time that the Renaissance era of the 1600s, which changed art and music and other aspects of culture, at that same time, people started conducting experiments and analyzing data in a new way. This was the beginning of what is now considered the scientific revolution, and it resulted in the gradual development of our understanding of atoms now. You guys know about the Renaissance? Development of art and culture, amazing pieces of art that were done. Michelangelo and Da Vinci, and those guys were active at that time. Galileo. So what we're going to do is we're going to fill in this chart, And all we have to do is find the name of the scientist who contributed this idea and when they did it. So for example, let's zoom through this. Where's Aristotle on here? Just skim through these different contributions. Where is Aristotle? What did he think? We just read about that. What did Aristotle say?
All matter was made because of earth and fire and water, right?
Excellent, yeah. So which one is that? Count for me. Fourth one down, huh? So this one's Aristotle. And that was 350 BCE. And actually, Democritus is on here too. What did Democritus do for us? What was his contribution to our understanding?
Adam,
What do you mean to atom?
first idea of an atom.
The first idea of an atom? Be careful on that one, because there's two of them that are pretty similar on there, right? But you're going to move on to the next page, which has basically these pages from your textbook that's describing the history of the atom and how that our ideas changed over time. So your goal is to study the diagrams to see how our ideas of the atom grew over time. Keep in mind that each of these views was supported by the evidence available at that time. Also notice how each new idea adds more details to the older concepts without completely rejecting the older ideas. It's not like we're saying, oh, Dalton was wrong when Thomson came along. It's just that we updated the ideas, huh? We improved them. So I'm going to give you a few minutes to read through these pages on your own. Find the guys' names on this chart and the time when they were working and fill that in. All right, so I'll give you a few minutes to work on that. So this is going to be pretty easy. Doing virtual Were you in Scary's class? Or were you just virtual first?
It's just completely virtual first.
Was that physical science?
I believe it was physical.
From Scary's class, or were you all virtual first? It was yours? I think you never did that. For Democritus, he was about the same time as Aristotle, maybe slightly before. You could say 400 BCE for Democritus. I'm wondering if he's the guy who also thought of the idea of democracy, and that's why we call it what we do, but I don't know. Question? Did you finish? Finish. the very last one on the chart. So not all of the scientists are included in our chart, okay? One I accidentally left out. Others, I just felt like their contributions overlapped a little bit, so I tried to separate them. Your hand up? Yeah. His big thing was that Rutherford's big contribution was the positive electric charge of the nucleus. He discovered that. So I think he put the right answer. Actually, I left Rutherford out, and that's one I added to the bottom. But that was after the fact, so. There's no other skipping thing. All right, so I'm gonna go over those diagrams, and maybe you should keep looking at the chart, maybe because you didn't finish it, or maybe because you want to check to see what I emphasize is what you're filling in. So once the scientific revolution began, the first guy to talk about the atom was John Dalton, and Dalton thought that it was basically what Democritus said, that it was a tiny particle that had no parts inside of it, huh? Little indestructible thing, no internal structure, nothing inside of the atom. That's what he thought. Pretty much the same as Democritus, huh? But Democritus invented the name of atom, right? And I think there's one on there that says came up with the name atom or something like that. So that should be Democritus. Next, almost 100 years later, Thomson, he discovered the electron. He was the first guy to find out that atoms had electrons. Now, he didn't really know exactly what they were doing. He thought they were just stuck into the atom. Like they compared it to plum pudding or maybe raisin bread or something with chunks of material surrounded by other stuff. Then a little while later, not much, a Japanese physicist, Nagaoka, he said, oh, there's a nucleus in the center of the atom, and the electrons are going around it, orbiting it like planets orbit the sun. The next contribution came from Rutherford from New Zealand, and he discovered the positive charge of the nucleus. Then we get to, it doesn't say where he's from. I forget. He's either from Sweden or Denmark, Niels Bohr. And his idea was that the electrons were orbiting around the nucleus, but they were at a constant distance from the nucleus. Now, they might be in different layers, but one electron would never change its distance from the nucleus. If it was in the first layer, it would always be in the first layer at that same distance. If it was in the second layer, always be that constant distance from the nucleus. And Bohr's idea of the atom is pretty much what we're going to focus on, even though there's more modern and updated versions. His is simple enough for us to be able to draw diagrams of it and stuff. Now later, de Broglie from France, or de Broglie from France, he said electrons also behave like waves. And remember, right at the end of our study of light, we talked about how light can either behave as a wave or behave as a particle, depending on the conditions. The same seems to be true for electrons. Sometimes they seem like particles, which is what we usually think of them. Sometimes they seem like waves. And then Schroeder came up with this idea that the electrons are not at a constant nucleus. Excuse me, they're not at a constant distance from the nucleus. They're moving around a little bit. They're more likely to be in this first layer, but they might move outward or inward from there. And this creates a cloud of electrons around the nucleus. And that they're unpredictable. It's hard to tell exactly where an electron would be at any moment. Partly because they're moving so fast. They're moving at a quarter of the speed of light. So incredibly fast objects. And then finally, Chadwick from Great Britain discovered the neutron. So you can see different scientists contribute to our understanding, and what we think about the atom has grown over time, huh? And it's still growing today. Now we think that protons and neutrons are made of even smaller particles called quarks. And we're going to study that one day too, probably later this week. Okay, so how are we doing on the chart? Did you finish? Let me see your gas tank. This is full. You're ready to move on. This is empty. You haven't started yet. You halfway there? You mostly way there? Are you done? So you need some more time a little bit? Okay, I'll give you a couple more minutes. He's not on there. No, I added him on for next year.
Me too. I literally had to
All right, let's move on. So we're starting with some background information here, and then we'll be moving on to more active things that we're doing. So what do atoms look like? Pull out your highlighter. And I love this t-shirt or bumper sticker. Never trust an atom. They make up everything. Get it? Little science humor for you. Today, we still agree with previous scientists that all matter is made of atoms. They make up everything. We have discovered 92 different kinds of atoms in nature, and these join together in different ways to make all of the materials around us. For example, water is made of two different kinds of atoms, hydrogen and oxygen, while sodium and chlorine atoms combine to make salt. All of the atoms are listed on the periodic table, which we will study later. Today's understanding of the atom can be compared to cutting a piece of aluminum foil into smaller and smaller pieces. Every little piece of foil still has all of the same properties as the original piece of foil. You can bend it and fold it, you can tear it, it's shiny, but it's getting smaller and smaller. It might be microscopic, but it is still foil. This is also true for atoms of any particular element. Even a single atom of gold is still gold. It has all the properties of gold. In addition, we know now that atoms are made of even smaller pieces called subatomic particles. We will focus on the three main subatomic particles, the proton, neutron, and electron. But keep in mind that we have also discovered that these particles are made of even smaller particles, such as quarks. So let's talk about this word subatomic particle. A particle is a little tiny piece of something, like a grain of sand would be a particle. But these are even smaller than that. Subatomic. Well, where does a submarine go? It goes underwater or inside the water, huh? Sub, when you put that in front of a word, it means under or within or inside. So what is subatomic? Inside the atom, smaller than an atom. Does that make sense? So if I ask you to name subatomic particles, I want these things that are smaller than an atom, that are parts of the atom. They're found inside the atom. Overall, an atom looks kind of like a tiny solar system. The nucleus is like the sun in the center, which has electrons orbiting around it like planets. The nucleus itself is made of a mix of protons and neutrons, which are approximately the same size as each other. On the other hand, electrons are much smaller. It would take almost 2,000 electrons to equal the mass of a proton or a neutron. So a proton is like 2,000 times bigger than an electron. But the neutron is the same size as the proton. Since these particles are so small, scientists measure them with atomic mass units, or AMU. They had to invent a new way to measure these tiny, tiny things, and what they came up with, they just call atomic mass units. Protons and neutrons both have a mass of 1 AMU, while the mass of an electron is only 1/1836 of an AMU, or 0.00054. That means it takes 1,836 electrons to equal the mass of a single proton, right? If it's 1/1836, tells you that it needs that many electrons to weigh the same as a single proton. The different particles also vary in their electric charges. Protons have a positive charge, electrons have a negative charge, and neutrons have no electric charge at all, which we call neutral. And that's where they get their names from. So when you start to memorize these, I suggest you go positive protons. They both start with P, huh? And then go neutral neutrons. And then what's left? The electron, which is negative. Okay? The names for protons and electrons also tell us something about them. The proton was the first particle discovered inside the nucleus, just like a prototype is a first test of a new technology. Proto means the first of something. So, when they're making new iPhones, do they just start selling them right away? Or do they build one and test it out? That would be the prototype. It's the first one. On the other hand, the electron also gives us the word for electricity. Electricity is a movement of electrons. So in this wire right here, there are electrons flowing through here. So that might help you remember those names. So your next task is to go through what we just read and use that information to complete this chart. So you have to name the 3 particles here. What are the 3 subatomic particles? After you've named them, tell me where they're found in the nucleus. Excuse me, where they're found in the atom. One of your options is nucleus, right? Are they found in the nucleus? Or are they found orbiting around the nucleus? Give me their mass in AMU. And then give their electric charge. Are they positive, are they negative, or are they neutral? So take a minute and fill in that chart. Yeah. Did you finish? I want you to finish this chart first. Oh, you didn't, that's all. Are you done? So I'm going to give you a little heads up. When you take a test, this is a question right here. It's going to look just like this. This chart is a test question. It will just say, complete the chart, but you won't have that information to use, will you? Instead, you'll have this information to use in here. I want you to memorize this chart. Okay? So let's make sure we did a good job of it. First of all, what are the three particles? Okay, electron, neutron, proton. Doesn't matter what order you listed them in. It doesn't matter what order you list them in. Okay, so just make sure that you're looking at the right row when I start talking about a particle. I'm going to start with the proton. So proton, where is it found? What's its location? Sorry? In the center, and what's the word for that, please? In the nucleus. You need to tell me it's inside the nucleus for the proton, inside the nucleus. What is the mass of the proton? 1 AMU, 1 atomic mass unit. What is the electric charge on a proton? Positive. Positive protons. Next, neutron. What is the location of the neutron? Inside the nucleus. Once again, in the nucleus. What is its mass? It's also 1 AMU. And what is its electric charge? Yeah, or you can just say neutral. That's why it has the name neutral. That's why it has the name neutron, because it is neutral. Or you can say no electric charge. You can just say none. It has, one way or another, it doesn't have an electric charge. So we have neutral neutrons, positive protons. What's the next one? Electrons. What's their location? Orbiting the nucleus. So they're flying around the nucleus just like we're flying around the sun. Orbiting the nucleus. What's the mass of an electron? Now, up in the text, it gives you very exact numbers, and I think those are harder to memorize. So when I look at this number, 1836, isn't that pretty close to 2000? All right. So for the mass of the electron, if you tell me it's 1 over 2000, that's good enough. Now, if you tell me it's 1 over 1836, I'll give you extra credit on the test. But to make it easier, just memorize that an electron is 2,000 times smaller than a proton. And protons are already pretty tiny, aren't they? Yet an electron is 2,000 times smaller than that. 1,836 times smaller than that, huh? And then the last thing, what's the electric charge of the electron? Negative electric charge. So how big is an atomic particle anyway? I should say subatomic particle. So imagine if we took an atom and we magnified it to the size of a football field. And that's where the electrons are orbiting, is at the goalposts. How big would the nucleus be in the center on the 50-yard line? Would it be as big as a house? Would it be as big as a car? As big as a horse? As big as a dog? As big as a squirrel? It's still smaller. The nucleus is only the size of a mosquito sitting on the 50-yard line, and there is nothing between that mosquito and the electron at the goalpost. In other words, an atom is almost completely empty space. Right here, that's almost entirely empty space. But because of the electrons, my hand is stopped, huh? because of the electrons in my hand and the electrons in this table, they can't pass by each other because they're both negative and opposites repel, the same charges repel one another, huh? So this is mostly empty space. And this water, well, that's soap and water, I'm not going to spray it, is mostly empty space, huh? Mostly emptiness, mostly nothing in there. Because every atom is only this mosquito and the electron is 50 yards away from it with nothing in between. So the nature of matter is so different than what we think of it is. This is mostly emptiness. Paper, mostly empty space. The air we breathe, mostly nothing. My brain, mostly empty space, right? Everything around us is mostly emptiness. Which is kind of strange. What if you could invent a way to travel through that empty space? All right, before we go on to page 5, let's just take a break from the project and go to the class notebook for a minute, okay? Did we already add unit 7 to the class notebook? Let's just make sure we're all good on your class notebook. Yeah. Are you ready? She'd asked before, so. Okay, I'll let you and her argue about who's gonna go first. Or I'll give you each I'll go get a scalpel from Tivo's room and you can fight it out. So in your chapter 7 notebook, or in your notebook, did you already create the new unit 7? I know I did that with one class. I did it with both classes then. And have you put a crime in the kitchen in there? Yeah. And have you put this unit project in there? Okay. If you've already done those two things, then your notebook should be in good shape. Page 1 would be the table of contents, right? Page 2 or page 3, I don't really care what order they go in. Crime in the kitchen. And then the unit 7 project, atoms in the periodic table. And then come back to the project. All right, let's go ahead and move on to page 5. So we're going to focus on how to make a drawing of an atom right now, how to represent an atom visually. And you can see on this page, there's a diagram of an atom of lithium already. A little more highlighting here. When we draw atoms, we simplify our diagrams by using slightly older ideas developed by Niels Bohr about 100 years ago. Our more recent understandings are more complex, and that makes them harder to draw because the exact location of the electrons are difficult to show within the electron cloud. But the Bohr model of the atom is still accurate in most respects, and so we're just going to use that as our method of drawing an atom. Your diagrams will need to include a key, like this one down here, which is incomplete. The key should show the three different kinds of subatomic particles. Then you draw the protons and neutrons together in the nucleus. Finally, add the electrons around the nucleus, showing their orbits around it. And I like to use a dotted line for that. So let's talk about that for a minute. Like when I drew this, I went up to my shapes, right? And I chose the oval shape. And I drew a circle. And then you know how to size the circle, correct? Well, how do you make it a dotted circle? You got to get into the properties. So right click, and then click on properties. It takes a minute to come up. And up here where it says style, that's where you can choose to make it a dotted line instead of a solid line. All right? So that's how you can make a dotted line to show these things orbiting. So look at this example of the lithium atom. There are a few details to notice, and these will be true for every atom that we draw in class. First of all, do you see that the protons and neutrons are spread randomly in the nucleus? It's not like we have the protons in one place and the neutrons in the other place. They're mixed together, aren't they? The blue and the yellow. The reason for that is because protons all have what charge? Protons all have a positive charge. And if it's the same charge, don't they push each other away? Don't they repel each other? And so in order to pack them together in the nucleus, it's kind of like we have to have some padding, and that's why we put the neutrons in there too. Next, would you agree in this diagram that the protons and neutrons are about the same size as each other? Because they're both 1 AMU. Next, there are usually more neutrons than protons. And that would help you make your key right here, huh? Which one is there more of, blue or yellow? So there's usually more neutrons. So I want you to add proton, neutron, electron to the key. There's usually more neutrons. So which is blue and which is yellow in the nucleus there? The atom is given a number that is equal to the number of protons inside it. We call it the atomic number. The mass of the atom is found by adding the number of protons and neutrons. Now look at this. It seems to me that in the lithium atom, which is symbolized Li, right? In the lithium atom, we have 3 protons and 4 neutrons. We also have 3 electrons. How many AMU would be found in those 3 protons? How many total AMU would be from the protons? Yeah, that would be 3 AMU. How many AMU from the neutrons? They're 1 each, aren't they? How many AMU from the electrons? A tiny fraction. Only 3/1836 of an AMU. Just a tiny amount, right? So this adds up to 7.0015. How much of that is from the protons and neutrons? All of this, huh? So when we're finding the mass of an atom, we pretty much ignore the electrons because they're so tiny, they don't really make a difference. Is that okay? Like, for example, let's see. You take your own weight, right? You cut off your hair before you find out how heavy you are? Because it doesn't make much of a difference for your weight, does it? Right? It doesn't weigh that much. It doesn't really matter. The same thing is true for the electrons. They're not heavy enough to matter when it comes to the mass of the atom. So we pretty much ignore them. So if I ever ask you the mass of an atom, just count up the protons and neutrons. What's the mass of lithium? Looks like 1, 2, 3, 4, 5, 6, 7 to me. Does that make sense? We just ignore the electrons. They're too small. They don't matter for the mass. Now they really matter for other things. But for mass, just count the protons and neutrons. Next, the electrons are shown orbiting the nucleus in different layers, which are known as electron shells. They're also called orbitals. They're also called energy levels. But these layers, these electron shells, are where we find the electrons. Notice that the electrons are much smaller than the protons and neutrons. How much smaller should they be? How much smaller should they be? Make me play a drum roll till you give me the answer. My hands are going to get tired, but it's good practice. How much smaller should they be? What's the number? I asked you to memorize it. Yeah, they're 1,836 times smaller, or you could say 2,000 times smaller. I don't know that that's 2,000 times smaller than that, though, is it? But within the limits of our ability to draw it, at least show the electron as being noticeably smaller. Now, what I like to do when I draw an electron, instead of using the circle, I just use the pencil and I draw a dot. And the way I do that is I make a pretty big dot. Like when I'm writing with the pencil, I often want this at one point, and it draws a line like this. But if I change this to 5, then it's easy to draw a single dot. And that I use for my electron. Okay? So I actually draw the circle for the proton and the neutron, and I change the color of it as needed by right-clicking, going to the properties. I think this one, the outside is black, and the inside, the fill color is blue. It wasn't that blue, though, was it? It was more of a blue like this, I think. So there's my, looks like one of my protons. Next thing to notice is the total number of electrons equals the total number of protons. Protons and electrons balance out in an atom. It's the same number of both of them. And finally, there are different numbers of electrons in each shell. We'll study more of this later, but for lithium, there's 2 electrons on the inside shell and 1 electron on the outside shell, making a total of 3 electrons, just like there were 3 of these blue protons. So as we did that, did you label the key? You put electron, neutron, and proton in there? Okay, so that takes us to this entry from the periodic table. Here we have 5 different terms that I would like you to label on this entry from the periodic table. Let's start with the easiest one. What's the element name? Yeah, so you can label the element name, I think, pretty easily as lithium. I'll cross that off. Next one, what about the element symbol? Symbol for lithium is Li. That one. So these symbols are used by scientists all across the globe, regardless of what language they speak. In India, they still use Li for lithium, even if they're speaking Hindi. Most of these symbols come from English, but not all of them do. And that's why you're going to see some that don't match. They're often from Latin words. Okay, next. Which of these is, what about that number 3 by itself? What is that? Yeah, good. So that number 3 is called the atomic number. And if you look back at this list of bullets, it's described right here. The atom is given a number, the atomic number, which is equal to the number of protons in it. Can you see that there are 3 protons in this diagram of lithium? So the atomic number is the number of protons. And that would just be the 3 there. So that was atomic number is this one. Next, atomic mass. Where do I find that? That is this bottom number. The atomic mass is going to be larger, and it's given in a decimal form. And we don't need to worry about that decimal form. We're just going to ignore the decimal, but I'll tell you why that happens. It turns out that there are different versions of atoms, and we call these isotopes. We'll learn more about the isotopes later. And the isotopes differ in the number of neutrons. So some lithium atoms only have 3 neutrons. They still have 3 protons, but they only have 3 neutrons instead of 4. But they're not very common. And so when we average together the masses of those smaller lithium atoms with the more common ones, the average turns out to be 6.94. So what we're going to do with these atomic masses is we're always just going to take the average of that. What's the average of 6.94? Excuse me, not the average. We're going to round it off. So how do we round off 6.94? What's it going to be? Is it just going to be 7? Which, isn't that what I found over here? Was it was 7? Right? So we're going to ignore the electrons, and we're going to round off when we have a decimal point to work with atomic mass. Finally, we get this. What does this represent? 2 and 1. These are the electron shells. Those are electrons. Now, what do we get when we add those together? 2 plus 1 makes 3. These should always add up to that. Should add up to the same thing. How many numbers are here? There's 2 numbers shown there, right? Since there's 2 numbers there, that shows me that I have 2 layers around my atom. I have 2 shells. The first number was 2, right? That tells me to put 2 electrons on the inside shell. And the second number was 1. So there's just 1 electron by itself on the outside there. So you should be able to take an entry from the periodic table and use it to draw a diagram of an atom. I'm telling you in advance that that is another test question that is heading your way. You're going to use the periodic table to draw a diagram of an atom. So you're going to practice right now with beryllium. You have to figure out how many protons does it have? How many neutrons does it have? How many electrons does it have? How many layers of electrons are there? How many electrons in each layer? And you should be able to do that by looking at 2 things. 1, our example of the lithium diagram, and 2, this list of bullet points over here. So use that information to draw a beryllium atom and include a key that describes what symbols you used for the protons, neutrons, and electrons. All right, so take a minute to do that, and please call me over if you get stuck. Oh, that's the key, right? Hey, another thing that you can do to make sure that your protons, neutrons, and electrons all look identical to one another, instead of drawing it over and over again, what I would do is click on that thing and copy and paste it. And then just drag it to where you need to be. That way they'll always be the same size. It would be weird to have a bunch of protons that are of different sizes, don't you think? So use copy paste. I like to use the keyboard shortcut, which is you hold the control button and you hit the letter C to copy. And then to paste, you hold control and you hit the letter V. And then you can make a whole bunch of those exactly the same size, shape, and color pretty quickly. Now, if you have a Mac, it's not Control C, it's Command C and Command V to paste. You can do the same thing with this dotted circle. Once you make a dotted circle, copy it, paste it, and then stretch it to be the size you want it to be. It makes it a little quicker that way. So this is where you're going to make a key. And this, you're supposed to label these 5 terms. Have to get labeled in the right part of the diagram. That's all you do for that. So you're going to tell me which of these is the atomic, is the element name. These are the 5 labels. Yes, good. Yes. Just put these names in the right place. So make sure you include a key that says 2 things. I didn't do this here, but I'm gonna do it now. So this is what your key should look like. I don't only want what the particle is, but I want to know how many there are. So include that in your key. This is what the key should look like for lithium. So in your key, tell me what shapes you used and tell me how many you made. bottom here. Drawing doesn't relate to this. And the keys. Yeah. Is this? Oh, you have to put this in. What? I think it shows up there for you. Your key down at the bottom should be like this too. Just tell me what shapes and colors you use. Yeah, you have to put it in on that. And fill this in too. Yeah. Yeah, here's the 5 labels. That you have to put in. Stay with me, buddy. Wait a minute. Huh. Okay, I see you filling in that key line, that's good. You also have to label these arrows. There's 5 names there, okay? And then let's see where you're drawing. So you're gonna put your drawing here, right? And then you're gonna make a key very much like mine, with different numbers, right? And maybe different colors. Good. Okay. Oh. Let's do this too. As soon as from somebody else, they will figure it out in time, but I couldn't later. So you were making the transition. Yeah. And then nobody changes to a dotted line. Yeah. So you're drawing those here?
Yeah.
And then each side goes here. That's what I was thinking.
That's the first I can do.
With a map?
How?
Sit that.
You would click on like the little.
See that? And now you can draw the dotted lines. But I think you have to.
I figured that out right now.
Oh, look, it just changed.
I just figured that out right now. Embarrassing.
You found the dotted line?
Yeah, like I've been like drawing. I literally figured it out.
Yeah. The diagram.
I've been wasting all this time.
Okay, I was gonna have you switched. See, you just repeated where it says key. And then with the diagram out here, but I don't care, it's one of the.
You can't really do something.
You have a question? There's your labels. Oh, you're gonna label those 5 arrows, well, one of them is a bracket. How many here? That's so- Looks right. You did this in I'm thinking that your diagram goes in the blank, and your key goes here.
Isn't it just like this
No, because that one has 7.
Yeah, it's a different element, so it's gonna have different numbers of particles. It's gonna be just like it, yes, but the number of protons, neutrons, and electrons will be different.
You don't even We just add one more.
So you're doing your drawing here and you're making your key there. You lost? Okay, you did good. Okay, so the diamond. So the blue is 3 protons, huh? What's the yellow? Also in the nucleus. Protons and what go in the nucleus? It says right here. Yeah, so how many are there?
Isn't there a little moral? Yes.
Okay, and how many black dots did I make?
Finish it all today.
And notice that it's the same as the number of protons.
What happened to the line?
So start with this.
Scares me.
I would never work on my.
Oh, I see.
Scares me when it comes to like,
Through
doing
line.
this. Like you like checking this. He's like, nah.
What I would prefer you do is to go through this. Four arrows. That one is atomic number. Good, good. Now, which one's the atomic number? No. Yes, yes.
No, yes, he's right.
And what does that mean? Yes. You said that?
I read like the first few chapters. Yeah, I do. I got that like chapter.
Good. Let's scroll up.
So you know how you
Okay,
really
now, you'll see this in the. Okay. Now, how would I find out?
I still have to do some of the characters. Oh yeah, I did. I did.
That
No, I
number.
read that it's like
How did I figure out that there were four neutrons? Yeah. There's minus traffic. First of all, that's seven. Minus three is. That's a lot of electrons. Yes. And how many layers? Well, there's two numbers, so I have two layers. First number was two, so I put two on the inside. And that's what you're gonna do for really. Yes. This piece of the diagram is
I know, like, vision, like this chapter.
yeah, black ball. You need
Yeah,
the
no, I
right
read that.
number of protons and the right number of neutrons. Okay? Use different emojis.
It really is a first chapter.
So if you want it, you can use different emojis. Or just draw a black circle and a red circle. It's good. Don't mention it. So I don't want you to undo anything because I haven't finished. Okay, so let's zoom out a little bit. So we look at both this and the diagram. Okay, so protons.
Yeah, that's the kind of point.
How come? How did I know from this thought? Do three. Right there, and it's not numbers. How many protons do you need to make a beryllium? Yeah. Now what about neutrons? And then we have just round that number off. Then subtract three. Doesn't three and four make seven? So you have to subtract.
I know it. Like,
9 minus 4.
and like,
Now, this is our electron shell. Since there's two numbers, I say two ways. How many electrons went on each side? And one on the outside. Honestly, a total of. Yeah, and lithium.
I know, whenever I'm like, sometimes sleepy, this, you know.
Actually, try to fix that.
I mean,
Hey, will you guys, in your key, tell me how many neutrons, protons, and electrons you made? Just like I did up there in the key for lithium, do that for the key for beryllium. Two elements, I like that you added that. I already saw yours. What's that red stuff? Oh, okay. Oh, I see what you did. Save it. Make sure you save your work, people. Yeah, I do. Save your work. On this. Okay. You still have to draw the nucleus though, huh? Okay, you know how many protons and neutrons you're gonna make? How many? 4 protons. How many neutrons? The neutrons are the tricky one, you guys. You have to subtract. To find the neutrons, you've got to go, you have to take the mass and round it off, and then subtract the number, and that will give your neutrons. Okay, so mass, round it off, subtract the number. Yes. And that's what you guys did. Did you know that's what you did?
No, I just know that there's more neutrons than protons.
Not always. Sometimes they're equal, but usually there's more neutrons. So you gotta subtract to find the neutrons.
that's why you do equations.
In this case, it was 9 minus 4 gives the neutrons.
But what if I did like 6 times?
So we said
Like, if I did 6
that was
times,
true of the
that's
lithium,
not,
but it's
yeah,
different
that's fine,
from
but
beryllium.
it's not the,
Okay. So let's look at this here. Let's go up to scroll. I want to see this and the diagram at the same time. So also zoom out.
So this number right here, that's how much you subtract out of
Just do that.
Oh,
Can you zoom out? Not zoom in, zoom out.
I just guessed.
Yeah, that's it. Get that out. Oh, yeah, that should work. Scroll down a little bit. I want to see that box.
That's what
and that
people just
diagram at
walk
the same
out.
time. Here's the other one.
Yeah, I never, I
Now, how many protons did I make? Where did I get that number from? Where's the 3?
Whenever it's there's like,
Yeah, like,
Isn't it right there?
it's like, that's.
That tells you there's 3 protons. When you look at beryllium, you have to see that number to see how many protons.
I've
Look
never
up there's 2 and
I've
1.
actually never asked, like, I only.
Yeah, that gave me my electrons. It's different from beryllium. Now round that up.
I've never asked.
7 minus 3 makes the 4 neutrons.
Yeah, exactly.
So you have to subtract to get the neutrons. And it's gonna be different for beryllium than it was for lithium. They're different things.
Yeah, that's funny because she was a little bit.
5 neutrons and 4 electrons.
How many electrons in each layer?
Oh, I'm sure.
In each shell. Make sure you save your work. You finished that?
Do she think homework or not?
Your numbers here.
What is the other?
That's good. You just have to follow through and make the diagrams. I would click on that and then just copy paste it.
Maybe you said.
Same thing for that.
When she asked, are you writing this?
Dude, that
I
was
was
so awful.
so embarrassed. I'm like, I was embarrassed. I was gonna say something. Why would you laugh? Like, that's
I love her after she's like throw the group chat. I was so awkward.
I should go to I was gonna, like, not even in the no, I was like, why would you put that on the group chat? And I was like, no, that'd be like weird. Well, yeah, I was gonna ask her, like,
I forgot that even though she was.
Make sure you save your work, people.
And then she thought and then I thought we were friends, but then I was so like,
I was like, just move.
Good.
Yeah,
Perfect. How many electrons total?
it's like very
Yeah. And then 2 layers of 2
if
each, right?
anything, she should have just asked her a postcard.
Wait a minute.
No, yeah, and like,
Put one of them inside.
and then when Elsie was like,
Oh,
Grab one of those to one side.
I was like, even worse.
There you go. 2 and 2.
She was I mean, she probably thought since like Jen invited her family, maybe she can invite you as she invited Jen. But I thought I was the only one.
So I told you about 2 different test questions you need to be ready for today.